Hi, my name is Courtney. In this problem, we're given the function f of x equals x plus 5 quantity squared. And we're asked to do the following. First, to sketch a graph of the function f. Then, to determine an interval over which the function is 1 to 1. And then to find the inverse function of f on that interval that we found in part B. And finally, to give the domain of that inverse function that we find. So let's start with part A, which requires us to sketch a graph of f of x equals x plus 5 quantity squared. So a couple things we might think about as we start to sketch this function. First of all, the parent function is going to be a parabola, f of x equals x squared. We can see the fact that we're adding 5 inside the parentheses means that we are going to be shifting that parent function 5 units to the left. So I'm expecting that rather than finding the vertex of the parabola at the origin, it's going to move over and be located at x equals negative 5. So this is where I'm picturing the vertex of a parabola that we know is going to still open upwards because it's going to take our basic parabola and simply shift it to the left 5 units. If we want to be careful about getting a couple of additional values correct as we sketch our parabola, we might check what happens when x equals 0. And I can see that when x equals 0, I'm going to have 5 squared or 25. And so my parabola should pass through this point. And I could use symmetry to check then that if I move 5 units to the left and plug in negative 10, I would have a negative 5 quantity squared, and I would get that same output of 25 over here at negative 10. And so, again, we already knew we had a parabola. This gives us a few guiding points to kind of sketch our parabola through. The parabola will look something like this. Pretty narrow here with the values that we have on our graph. But we end up with a parabola such as the one that we've sketched here. Next, we need to determine an interval on which this function f of x that we just sketched is going to be 1 to 1. Now remember what it means to be 1 to 1. From a graphical perspective, being 1 to 1 means that a graph would pass a horizontal line test. And we can see right now that this function certainly does not pass a horizontal line test. Almost any horizontal line that we place is going to intersect the graph in 2 places, meaning that it is not 1 to 1. There are 2 inputs with the same output. So we want to know, how could we restrict this function so that it is 1 to 1 and keep the domain as large as possible? Well, there's really 2 ways we can do it. We could either work to the left of the vertex or to the right of the vertex. Generally speaking, I think it makes sense to work to the right to keep values as positive as possible. So perhaps we just take this portion of our function. Notice now, if we restrict to the portion of the function that I've highlighted blue, and we can take the vertex with it, so I'll highlight that blue just for emphasis, any horizontal line that I now sketch will only pass through the blue portion of that graph at most once, because we've eliminated this sort of reflective piece over here that was causing some problems before. So, if we want to go back then and determine an interval on which f is 1 to 1, well, one such interval, and in fact an interval that keeps the domain as large as possible, would be the interval from negative 5 all the way to infinity. Because remember, this graph continues and continues even over here into the positive direction. So one interval that we could choose would be the interval from negative 5. And notice that I am purposely including that x value of -5 because we said it's okay to take the vertex. We just can't go at all to the left of it. Otherwise, we're now failing the horizontal line test. The function would no longer be 1-to-1. And the x values can continue forever in the positive direction. And so one such interval would be -5 to infinity, where -5 is included. It's possible that you were thinking of taking the other part of our graph. And so I do want to note that it would have been okay here. We'll stick with this one. But if you were thinking perhaps that you could have chosen the interval from -infinity to -5, that absolutely would have worked here as well. Okay, so now that we have taken our function, we've broken it down to a smaller interval on which it's 1-to-1. Now it makes sense to find the inverse function of f on that interval. Remember, the important thing here is that we can't find an inverse function until we've started with a 1-to-1 function to begin with. So that's why that first step was so important for us. If we restrict to this interval, we should now be able to find an inverse function on that interval. So how do we do that? Well, let's start by expressing the equation that we were given here. We have y equals x plus 5 quantity squared. Now, before I go too far with this, I want to be a little bit careful that I'm only thinking about the part of this function that we've highlighted in blue here. And so let's think about making sure that we're working with the correct x values, those from -5 and bigger. And so in order to do that, I'm going to actually solve this equation for x. So in order to solve this equation for x, I would begin by taking a square root of both sides of my equation, since x plus 5 is currently being squared. If I take a square root of both sides of my equation, I recognize that when I do that, I will have x plus 5, taking the square root of x plus 5 squared, and that will equal plus or minus the square root of y, being careful that we capture both possibilities since we're taking a square root of both sides of the equation. Why is this helpful? Well, now if I take this equation and I solve it for x, I see that x then is -5 plus or minus the square root of y. Remember, this is still an equation that represents the function that I started with. I haven't yet found an inverse, but I've solved for x. And the reason this is important is because if I'm only focusing on the blue highlighted portion of this graph, I only want x to be bigger than -5 or equal to -5. And so if I think about this equation, the blue portion of my graph here, so I'm going to use blue to indicate now that we're just focusing on that 1-to-1 piece, it would only be values -5 and bigger. And so I don't want to subtract a positive value from -5. I only want to add a positive value. So I can focus only on this part of the equation. X will equal -5 plus the square root of y for the blue portion of the graph. The part that is unhighlighted would be the part where x equals -5 minus the square root of y, because we'd be subtracting a positive value from -5, giving us values of x even less than -5. So this has expressed our equation for the original function just in terms of the blue highlighted portion, focusing solely on our 1-to-1 piece. Now we're ready to find the inverse of that piece. How do we find an inverse? Well, remember, once we know an inverse function exists, which we're to the point where we know that it does, in order to find it, we interchange our x and y values. And so within this equation, to find an inverse, I am going to swap out where I saw an x and where I saw a y. So for the inverse function, we would get that y equals -5 plus the square root of x. So if we want to express this inverse in inverse notation, we could also write this as f inverse of x equals, and I might want to put my variable term before the constant while I'm at this. So I'm going to write this as the square root of x minus 5. So at this point, we have found an inverse function that represents just this portion of our original function over which it was 1-to-1. Finally, we are now asked to find the domain of that inverse function. So we could stop and actually analyze the domain of this function, and in just a moment we can check ourselves that way. But the important thing to remember is that when we're talking about inverse functions, domains and ranges switch. And so if we look at this portion that we restricted here, if we look at, I'm going to use blue to represent that piece, recall that its domain, our restricted domain for this portion that was 1-to-1, we said was -5 to infinity, where -5 was included. And its range, if we look at the y values that this function takes over that domain, it looks like the smallest value it ever takes is 0, and it does reach 0 when x is -5. And the values will then increase without bound. So the range of the original function f of x with our restricted domain is 0 to infinity. That means when we come over here to answer our question about the domain of the inverse function, that should correspond to the range of the original function. And so we're able to answer this question without even looking at our work above, but going back to the graph and our work here, which says, well, that range of the original function was 0 to infinity, including 0 as a possible output. Let's just check this quickly. If we think about what our inverse function actually turned out to be, and we want to sort of make sense that the domain of this inverse function is in fact 0 to infinity, think about what could go wrong in this inverse function. We see a square root. We know that we can plug 0 into the square root, no problem at all. If I plug 0 into my inverse function, I'll get an output of -5. And I can plug anything larger than 0 into that function, but I can't plug negative numbers in there. And so that's just kind of a nice way to check that the domain of our inverse function is in fact 0 to infinity, 0 included, but we were able to generate that by just looking at the range of the original function that we were given. Great job persevering through this problem on a function and its inverse. Now you're ready to get some more practice on your own.